There are a few questions which related to this butane-dione monoxine BDM. When is this a good guy and when is it a bad guy? So it's primarily used as an inhibitor of myosin type 2 ATPase. So it stops the cross-bridge cycling process in myocytes. So the concept here is that BDM will improve the survival of the cells during isolation. This has been known for many decades, well, I think 3 decades now, and in culture as well. So I've just put up a figure from a paper back in 1998. This is looking at hypercontraction of myocytes in culture, and you can see when you increase BDM concentration, you have reducing hypercontraction. This is an idea of reduced contractility, and because the ATPase is being inhibited, you're having reduced ATP consumption, therefore reduced metabolic demand. You have reduced calcium paradox. This is this idea that when you reintroduce calcium to myocytes after isolation, you can actually have influx of sodium and calcium into the cells, which then leads to problems such as hypercontraction. So BDM, especially during isolation, is really good for preventing this, and it's quite cheap as well, which is another advantage of it. However, of course, BDM can interfere with the physiological functional properties of cells, such as calcium and electrical properties. And it also has non-specific phosphatase activity. So certainly for functional assays and also for biochemical signaling assays, it's quite important to remove BDM from your system before you do these assays. And this can be quite easily done during the calcium reintroduction, which I think Davor might discuss later, but this is where effectively gravity settle the myocyte isolation product 4 times through increasing buffers with increasing calcium concentration. And while you're doing that, you can actually use a second buffer which has no BDM in it. So effectively using thyroid buffer with no BDM or culture media with no BDM. And so at the same time then, as you are increasing your calcium concentration, you're decreasing your BDM concentration. So at the end, you'll have cells which are in physiological calcium concentrations and without BDM. And that's one quite simple way of doing it. When it comes to cell culture, I'll put a note here, which I might come on to later, but just to say that we actually don't use BDM in our culture media anymore, or our plating media anymore. We switched to blebistatin. We think it's cleaner. It's a bit more expensive, so we don't use blebistatin for our actual isolation buffers, but it's also a myosin ATPase inhibitor, so it stops contraction. It does a very similar thing to BDM, but with less, we think, of off-target effects. And 5 micromolar for us seems plenty to give you very good yields of rod-shaped cells in culture for a number of days. But of course, similar to BDM, you would have to remove blebistatin before you do any functional assays. It would otherwise your contractile properties of the cells would be compromised. If anyone has anything to add on there, then please go ahead.
I would just say that I obviously agree with everything that Matt's just said, and in fact we do in my lab, we do a lot of optical mapping experiments as well. So we need to uncouple the contraction in order to monitor voltage changes or calcium changes, and actually we wouldn't use BDM for those experiments because it really interferes with the electrophysiological properties of the heart. So blebistatin is certainly a better choice. And 5 micromolar to 10 micromolar is the region that tends to be used in the literature generally for uncoupling the contractile artifact from the optical mapping setups. So this seems that you're in the right ballpark figure for me to essentially uncouple the myofilaments.
Yeah, I also agree on that. And in ourselves, we actually don't using either one of them. And so I think we try to prevent potential confounding effects physiologically and biologically. And since we have been okay to get away with it, so, I think if we don't have to use it, I think that would be the best.